January 1911. Snow hammered the western slopes of the Rockies so hard it muted the world into a white silence. Somewhere below that silence, a crew of men stood at the mouth of a half-finished tunnel, staring into a black void carved into the mountain. Their lanterns flickered against walls of raw granite. The air was thick with dust and the smell of blasting powder. No modern machinery, no hydraulic drill rigs, just steel rods, heavy sledgehammers, dynamite, and the stubborn will to break a mountain wide open. What they were building wasn't supposed to last 10 years. It wasn't supposed to require constant patching, flooding control systems, or emergency shutdowns. The engineers who designed these early rail tunnels had something else in mind, something we rarely see today: permanence. They expected their tunnels to outlive them, outlive the railroad, maybe even outlive the century. That demand for longevity wasn't creative optimism, it was business. A tunnel that collapsed was more than a structural failure. It meant trains delayed for days, coal shipments stuck at the wrong side of a mountain, and reputations ruined. So they overbuilt every square inch, not as a luxury, but as survival. And somehow, impossibly, those decisions made in the cold dark of 1911 still echo through the mountains today. Because many of those tunnels, they're still here, still carrying trains, still dry, still strong, still standing against the same forces of nature that should have pulverized them by now. Meanwhile, many modern tunnels with computerized moisture sensors and concrete pumped by laser-guided machinery start failing within a decade. How did the men of the 1910s, working with primitive gear, build tunnels that outlast ours? To understand that, we need to step back into the mountain and walk deeper into the darkness where their methods and their mindset still live. In the early 1910s, American railroads were locked in a brutal competition. Speed mattered. Reliability mattered more. A tunnel was a billion-dollar asset in today's terms. If it failed, it wasn't just a repair cost. It could shut down an entire region's supply line. So railroad companies did something modern contractors rarely do. They invested in durability first. Engineers insisted on thick concrete linings, not thin shells. They demanded stone portals with massive granite blocks carved and set by hand. They required deep drainage channels chiseled directly into the mountain floor long before the first train rolled through. And they didn't compromise when finances got tight, because the entire company's future rested on these tunnels holding strong. But more than money fueled this overbuilding. It was pride. You can hear it in the letters of railroad engineers from the era. They talk about building for posterity, about works that must endure for ages. These were men raised on cathedrals and bridges of stone, not disposable structures with a planned lifespan of 3 decades. And so their design philosophy was simple. If it's underground, it must be eternal. That philosophy shaped everything. Tunnel crowns were poured in multiple layers of hand-mixed concrete, each cured fully before the next was applied. Lateral walls were so thick that future engineers would measure them and think the original builders were insane. Drainage gutters were carved wide and deep, sloping precisely downward to natural outlets. They didn't rely on pumps. Pumps fail. Gravity doesn't. This combination, money, pride, engineering caution, created a blueprint for tunnels that could survive not just decades, but geological ages. And all of it was built by thousands of workers whose methods were slow, dangerous, and astonishingly effective. Picture the work shift. A crew of 30 men step into the mountain at dawn. Their boots crunch over loose stone. Their breath fogs in the cold air. Each man carries steel drill rods, hammers, and little else. There are no electric lights, no roaring machinery, just flickering oil lamps and candles that throw trembling shadows against the rock. The air tastes like stone dust, sweat, and the faint metallic tang of dynamite residue. It is heavy, stale, and every inhalation reminds you that you're deep inside the earth. At the tunnel face, the real work begins. Two men brace a drill rod against the solid rock. A third man positions himself behind them, feet wide, sledgehammer in hand. He swings. The hammer crashes into the rod with a bone-cracking clang that echoes for what feels like miles. Dust sprays outward. Without a word, one of the front men rotates the rod a quarter turn. Another swing, another turn, another swing. This continues all day, hole after hole, foot after foot. Strike, turn, strike, turn, until their arms shake uncontrollably. This brutal rhythm was called hand steel. It was agonizingly slow, demanding strength, stamina, and perfect timing. But it was also incredibly precise. Every drilled hole had a purpose, part of a blast pattern designed like a puzzle. Each stick of dynamite would break the rock just so, without destabilizing the surrounding mountain. Once the holes reached their depth, the mood shifted. Dynamite sticks were carefully packed inside, tamped with clay, wired to the blasting circuit, and triple-checked. Workers retreated into the darkness, oil lamps still trembling from the tension. The foreman called out. A moment of silence. Then a thunderous eruption shook the whole mountain. Dust belched from the tunnel mouth. The ground vibrated under their feet, and then, as always, the men walked right back in. The blast didn't mean progress was finished. It simply meant the next phase could begin. They inspected the newly fractured stone, removed loose slabs, shaped rough edges, and ensured the rock face was stable enough to continue. Nothing was rushed. Nothing was ignored. Only then did the lining crews move in. Carpenters built massive wooden forms by hand, setting the curvature of the tunnel. Behind them, workers mixed concrete on site, cement, aggregate, water, sometimes with small steam-powered mixers, sometimes entirely by shovel. This wasn't high-tech concrete loaded with additives. It was simple, honest material, placed with care. And they placed a lot of it, 2 feet thick in places, sometimes more. Steel reinforcement was added, bars thicker and heavier than what most modern projects would ever consider. And then they waited. They let the concrete cure fully, refusing to push forward until the structure was ready. Progress was slow, almost stubbornly slow. Some shifts gained only a few feet. But every inch received attention, bordering on obsession. The result was extraordinary. A concrete lining that bonded so tightly with the surrounding rock that it behaved like a single geological formation. No air pockets, no weak spots, no rushed pores, just solid, uniform mass. These tunnels were carved by force but finished with finesse. That combination, violent excavation followed by meticulous refinement, created structures rugged enough to withstand earthquakes, floods, and a century of weather. Tunnels that modern engineers still marvel at. Tunnels that refuse to die. When the first trains finally roared into these tunnels in the 1910s, something unexpected happened. Or rather, something didn't happen. Nothing shifted, nothing cracked, nothing leaked. The tunnels didn't groan under the weight of locomotives or buckle under the heat of steam. They didn't shed dust from vibrations or drip water from unseen fractures. They simply held, as if the mountain itself had grown around them. Decade after decade, as the world changed, the tunnels remained uncannily unchanged. Engineers would walk through them in the 1930s, the 1950s, the 1970s, clipboards in hand, expecting to find the usual signs of aging: concrete spalling, water infiltration, structural deformation. Instead, they found stillness. The stone portals, carved from thick granite blocks, resisted freeze-thaw cycles like ancient monuments. Every winter, moisture froze in the joints, expanded, thawed, and yet the portals barely moved. Modern portals, thin precast concrete frames, tend to crack like eggshells under the same punishment. But these older ones, they were overbuilt fortresses. Inside the tunnels, the thick, multi-layer concrete linings absorbed stresses modern tunnels would fail under. The walls weren't single pores, they were layered coats of carefully cured concrete, bonded to stone that had been hand-shaped before the pour. The contact was so tight that the tunnel and the mountain became one continuous structure. Any stress the mountain exerted, any shift, any flex, any seasonal pressure, it didn't strike a weak point. It dispersed across mass, mass upon mass, layer upon layer. Modern engineers call this redundancy. The 1910 builders simply called it good work. But the most overlooked reason these tunnels still survive? The drainage systems. They weren't just clever, they were brilliant. The workers didn't rely on pumps. Pumps fail. They didn't rely on complex piping networks. Pipes clog, crack, burst. Instead, they carved channels directly into the tunnel floor and walls, simple grooves in the rock that sloped downward, always toward daylight. These channels were wide enough for a man to clean with a shovel and deep enough to handle seasonal storms. And because they followed the mountain's natural contours, water never had a chance to accumulate pressure behind the lining. It always found an exit. Gravity did the work. Gravity never gets tired. In many modern tunnels, inspectors can follow water trails like veins. In the old ones, they often find nothing, just stone, dry stone. Some tunnels are so dry inside that they feel like being inside a building, not a mountain. A century of snowmelt, rainwater, storms, groundwater shifts, and not a single drop makes it through the lining. Engineers with moisture meters walk through expecting chaos and instead find stability bordering on absurd. And that's when it becomes obvious. These tunnels didn't just survive time, they defied it. Consider the forces that have acted on them. The mountains pressed from the outside, the trains pounded from the inside. Temperature swings expanded and contracted the rock. Moisture attacked from every angle. The earth shifted. Seasons changed. Rail traffic evolved from light steam locomotives to heavy diesel engines weighing hundreds of thousands of pounds. Every factor that should have destroyed these tunnels only proved how well they were built. And the difference isn't magic. It's not geological luck. It's not a unique mountain or mineral composition that favored them. It's mass, it's thickness, it's redundancy. It's a construction philosophy that believed it was better to build once and build right than to return every decade with repair crews and budgets. Modern tunnels are engineering masterpieces, but they're optimized, calculated, efficient. They meet the minimum required safety standards. Nothing more. That's not laziness, that's economics. But a tunnel built with minimum in mind will always lose to a tunnel built with forever in mind. The 1910 builders didn't shave off inches of concrete to save cost. They didn't lighten the rebar grid to hit a deadline. They didn't skip drainage channels because the mountain was probably fine. They didn't rely on pumps that could fail. They didn't assume modern concrete additives would fix everything. They built with a paranoia that bordered on reverence. And the results from that mindset are all around us today. Through a century of storms, earthquakes, landslides, fires, and relentless train traffic, these tunnels stayed standing. They barely aged. Some didn't even develop cosmetic cracks. They are, in many ways, monuments to overbuilding, a concept modern engineers admire but rarely get to practice. Walk into one of these tunnels today and run your hand along the wall. You'll feel cold, smooth concrete poured before World War I. You'll see a stone portal that hasn't flinched since the Titanic sailed. You'll breathe air that hasn't been damp in 100 years. It feels surreal, almost wrong, like man-made structures aren't supposed to last this long. But these did, because they were built to be permanent. And permanence, once carved into a mountain, is a hard thing to kill. Across the American West, There are tunnels from the 1910s that sit inside unstable mountains in regions hammered by rain, snow, and seismic shocks. Any modern tunnel built there would require constant repairs, monitoring, and millions in upkeep. Yet these older tunnels still operate with barely any intervention. Some sit beneath slopes that slide every spring, but the tunnels hold. Some lie under peaks that shift in freeze-thaw cycles, but the concrete simply flexes slightly and resettles. Some experience floods so intense modern crews would panic and shut everything down, but the old drainage channels whisk the water away as if nothing happened. These tunnels have endured locomotive impacts, derailments, earthquakes, wildfires, even the occasional blasting for nearby mining. And through it all, they remain stubbornly unbreakable. Modern engineers who study them often come away baffled. They measure the wall thickness. They examine the hand-cut stone. They look at the decades of geological pressure, and they realize something humbling. The builders didn't underestimate nature. They over-prepared for it, by miles. Now, compare all of that with modern tunnel construction. Today, when a tunnel project begins, the first thing engineers look at isn't the mountain, it's the calendar. The second thing? The budget. Before the ground is even touched, before surveys are done, the project already has a deadline, a fixed completion date, a ribbon-cutting ceremony scheduled years in advance. Every step must bend to that schedule, and that single decision is where the cracks begin, long before they appear in the concrete. Modern crews work under pressure the 1910s builders never felt. Contractors are penalized for delays. Workers are incentivized for speed. Engineers must balance their ideal design with what the client is willing to pay for. It creates a world where decisions aren't made for durability. They're made for deadlines. So tunnel linings get thinner. Not because engineers want them thin, but because concrete is expensive, and pouring it thick takes time. Crews pour fast, cure fast, and move on. Modern high early strength mixes allow this, but they also shrink, crack, and weaken over time far more than the century-old formulas. Drainage systems? They don't follow the natural shape of the mountain anymore. Instead of carving deep gravity-fed channels directly into the rock, because that would require excavation and precision, modern tunnels install electric pumps and pipe networks. It works well for a while. Until a pump fails, until sediment clogs a pipe, until groundwater pressure builds where it shouldn't. And when water builds up underground, it doesn't politely wait for maintenance day. It pushes, it expands, it finds weaknesses, and modern tunnels with their thinner linings and rushed construction joints give water far more opportunities. Rebar tells the same story. In the early 20th century, rebar was heavy, overbuilt, and spaced at densities modern crews consider unnecessary. Today's rebar is lighter, not weaker individually, but used in less abundance, calculated right up to the required strength with little margin for the unexpected. In engineering terms, it's efficient. In geological terms, it's optimistic. And then there's the concrete itself. Modern concrete is a technical miracle. Admixtures, accelerants, plasticizers, perfectly graded aggregates. It can be pumped hundreds of feet, sprayed onto walls, or set in forms with robotic precision. But that convenience comes at a cost. High-performance mixes dry fast, cure fast, and lose water fast. And what dries fast, cracks fast. Microfractures form inside the lining that inspectors can't see. Thermal stresses build. The structure becomes less forgiving. At first, everything looks fine. The walls gleam under new LED lighting. The smooth finish makes the tunnel feel futuristic. Cars and trains pass through it like it's a piece of tomorrow. But behind those walls, the problems are already forming. Moisture seeps through microcracks, leaving thin white veins of mineral deposits, harmless at first, until the water finds rebar. Corrosion begins invisibly. Rust expands the steel, creating internal pressure that pushes outward against the concrete. Tiny cracks become wider. The lining loses strength. Water enters more freely. And once water enters a tunnel lining, it has a way of never leaving. The drainage systems, so dependent on pumps and pipes, need constant maintenance. A single power outage turns a brand new tunnel into a bathtub. We've seen it again and again. Tunnels flooding after storms, dripping like caves, walls stained by groundwater just 5 or 10 years after opening. And then winter arrives. Freeze-thaw cycles are a silent killer. Water inside the cracks freezes, expands, fractures the concrete, melts, then enters deeper. Each season drives the moisture further into the lining, undermining sections that were borderline from the moment the forms were stripped. Before long, the maintenance crews are called in. Inspections detect anomalies. Contractors are hired to seal leaks, patch cracks, inject epoxy, repaint surfaces, replace pumps, unclog drains, millions spent just to keep the structure functioning. All of this for a tunnel barely a decade old. Not because the engineers were wrong, not because the workers were sloppy, but because the system they worked inside demanded speed over strength. The old builders weren't better engineers. They were better positioned to ignore the clock. They didn't have shareholders demanding faster completion. They didn't have public officials promising grand openings before the next election. They didn't have supply chain pressures or environmental impact assessments locking them into specific timelines. They had time. And time is the one resource modern tunnel construction rarely has. When you build slowly, every layer cures fully, every joint bonds properly, every wall gains mass, not just enough to stand, but enough to endure. Slow construction leads to thicker concrete, thicker stone portals, thicker walls that resist not just today's stresses, but tomorrow's. Modern builders know how to build like that. They just aren't allowed to. And so modern tunnels, engineered with precision and software and advanced modeling, often crack, leak, and demand repairs within 10, 15, 20 years. Meanwhile, the old tunnels, built with hand tools, dynamite, and patience, are still carrying trains a century later. It isn't intelligence that separates the two eras. It's not technology. It's not skill. It's philosophy. Build it fast, or build it forever. The early engineers chose forever. We choose fast, and that one decision, made before a single shovel touches the ground, changes everything. The century-old tunnels still operating today carry more than just freight. They carry a legacy of stubborn craftsmanship. They prove something modern infrastructure keeps forgetting. Durability is a choice. When you slow down, build thick, use the natural geology as an ally rather than fighting it, and design for the next century instead of the next decade, you get tunnels that become part of the mountain itself. The early rail tunnels outlasted the companies that built them, outlasted the steam locomotives that first passed through, outlasted the political fights, the economic collapses, the shifts in technology, the changes in ownership. They're still there, deep inside the earth, unbothered by time. And now, more than 100 years later, they quietly embarrass us. They're proof that building strong doesn't require advanced technology, just patience, care, and the refusal to compromise. The tunnels of the 1910s were born in darkness, built by hand, carved out by men who swung steel into stone until sparks flew. And yet their work remains, as solid as the mountains themselves. In an era where flood-prone, crack-prone, maintenance-heavy tunnels are considered normal, these century-old giants remind us of a different philosophy. One that asks a simple question: if we can build it once, why not build it to last forever?